Hello everyone, my name is Zhang, and today I will deliver a presentation that mainly focuses on the state-of-art technology, 5G. So what is 5G? 5G is the fifth generation mobile network. It is a new global wireless standard after 4G networks. 5G enables a new kind of network that is designed to connect virtually everyone and everything together, including machines, objects, and devices. 5G wireless technology is meant to deliver a high multi-gigabit per second peak data speed, ultra-low latency, more reliability, massive work capacity, increased availability, and a more uniform user experience to more users. Higher performance and improved efficiency empower new user experience and connects new industries. So for this topic, I will cover the following six parts. First is the motivation of 5G. Second is the roadmap to 5G network. Third is requirement for 5G. Then the technology that used in 5G. 5G, what is 5G applications, and what we can expect in the future for 5G and 6G. So over the past decades, the demand for higher data rate has been continuously growing to satisfy the consumer's desire for a faster, safer, and smarter wireless network. The industry of wireless communications has experienced a great evolution in efforts of boosting system performance and data rates. However, a significant paradigm shift is required to further strengthen the wireless communication network since the current wireless system are facing a bottleneck in spectrum resources, which makes it difficult to enhance performance in the limited available bandwidth. The industry has predicted that in order to reach the network level capability of serving more users with higher data rates, more spectrum resources are required to be allocated for the next generation of wireless communication networks, and current spectrum needs to be utilized more efficiently. Moreover, small cells and ultra-dense network will be deployed to make the network more flexible and to provide more user with network connectivity at anywhere at any time. Additionally, new wireless access technologies should be backwards compatible with the existing solutions to obtain the optimal network performance with faster data rates, which ultimately leads to the driving forces towards the fifth generation wireless communication network. So before we dive into the detail of 5G, we can first look at the development and roadmap to 5G. So first we're going to talk about 1G. 1G was analog telecommunication standard introduced in the 1980s for voice communication with a data rate up to 2.4 kilobits per second. It used FM and FDMA and a bandwidth of 30 kilohertz. The major problem with 1G are poor voice quality, poor battery quality, and large phone size. 2G was digital standard circuit switching technology introduced in 1990s. It used CDMA, GSM, and TDMA technologies. It could only transmit digital voice at 64 kilobits per second and no data such as email. Next comes 3G wireless systems, which are still in use today, but normally when the superior 4G signal fails. 3G network use code division multiple access technology. It introduced high-speed internet access. It used technologies such as WCDMA and HSPA, which stand for high-speed packet access. It provided IP connectivity for real-time and non-real-time services. The development of 3G was mainly driven by the demand of data services over the internet. 4G network is the same as 3G and may be regarded as an extension of 3G but with a faster internet connection, more bandwidth, and a lower latency. 4G technology such as LTE, which stands for long-term evolution, claims to be about 5 times faster than 3G services. There are some challenges that cannot be resolved by 4G. This includes spectrum crisis and high energy consumptions. There have been drastic improvements from 1G to 5G. And here's the figure that shows the generation of wireless technology from 1G to 5G and the timeline and what application that we have for the different generations of networks here. Okay. So what is the technology evolution? The 1G, as I mentioned before, uses the FDMA, which stands for Frequency Divided Multiple Access. So FDMA allows multiple users to send data through a single communication channel, such as a coax cable, or microwave beam by dividing the bandwidth of the channel into separate non-overlapping frequency subchannels and allocate each subchannel to a separate user. A user can send data through a subchannel by modulating it on a carrier wave at the subchannel's frequency. It is used in satellite communication systems and telephone trunk lines. And 2G and 3G both use CDMA and GSM. GSM transforms calls into digital data, gives them a shared channel and time slot, and put the pieces of each call back together for the listener on the other end. CDMA encodes each call's data with a unique key. Then all calls are transmitted at once, with receivers dividing the combined signal back into individual calls. So of the two, GSM is more widely used around the globe, with availability in more than 200 countries. One major distinction between GSM network and CDMA network is that the former allows you to make voice calls and transmit data at the same time, while the latter does not. GSM and CDMA standard apply to 2G and 3G connectivity, but in the 2G era, network can only transmit digital voice signals, and the data rate was around 64 kilobits per second. And when the things evolve to 3G, 3 megabits per second data rate can be achieved, and the user have the ability to download documents, images, and videos within a few minutes. So let's go to the 4G LTE. So LTE stands for long-term evolution, which is the standard for wireless broadband communication for mobile devices and data terminals. LTE was first proposed in 2004 by a Japanese mobile network operator. LTE is based on GSM technology, and it increases the capacity and speed using a different radio interface together with core network improvements. The LTE wireless interface is incompatible with 2G and 3G networks, so that it must be operated on a separate radio spectrum. 4G LTE network is available to handle download speed between 5 and 12 megabits per second and upload speed between 2 and 5 megabits per second, with peak download speed approaching 50 megabits per second. LTE has the ability to manage fast-moving mobiles and support multicast and broadcast streams. LTE supports scalable carrier bandwidth from 1.4 MHz to 20 MHz and support both frequency division duplex and time division duplex. So before we go into what technology is used in 5G, we can first look at what's the requirement of the 5G. So the first requirement will be the high data rates. With the emerging applications demanding higher data rates, such as the Ultra HD 4K video streaming, 5G networks are expected to have the peak data rate of around 10 gigabits per second, which is 100 times improvement over the current 4G networks. So for the worst case data rate user can experience, the 5G should also be improved to 100 megabits per second, which is also 100 times improvement over the 4G network. And second requirement is low latency. The round-trip latency of data planes in LTE network is around 15 milliseconds. However, for the recently emerging applications such as the virtual reality, the multiplayer gaming, and autonomous driving that 5G network can expect it to support, the latency should be upgraded to an order of magnitude faster than the current network, around 1 millisecond. The third requirement is the low energy consumption. The 5G network are expected to support IoT devices. These devices are mostly low power, low cost devices with lifespan as long as several years. With the increasing number of connected smart devices, the number of base stations required to support this device will also escalate. Because of the deployment of small cells, the base station will be densified. This foreseeable trend demands the base stations to be energy efficient, since even a small improvement in energy efficiency will translate to a huge energy savings in a large scale. And there's other requirements for 5G, including the high scalability, the improved connectivity, reliability, and the improved security. So how does 5G work? While while current technologies are working so far, they are not an optimal approach when the subject is 5G. New modulation and coding schemes are being exploited, and some of them already have shown decent results. 5G use 5G new radio air interface alongside with massive MIMO technology. 5G also uses wider band technology such as sub 6 gig and millimeter waves. 5G are supposed to have two architectures, the SA and the NSA. So now let's talk each of them. So what is sub 6 gigahertz and millimeter wave? So strictly speaking, millimeter wave refers to radio frequency spectrum above 24 gigahertz. But particularly speaking, and in the context of 5G, 6 gigahertz can be seen as a division line for millimeter wave. Spectrum above 6 gig is a millimeter wave, while spectrum below is not. Propagation can vary significantly between low and high frequencies. Low frequency spectrums, including the sub 6 GHz, can transfer farther and penetrate solid objects like buildings better than the high frequency spectrum like millimeter waves. The current spectrum utilized for the mobile communication is mostly situated below 6 GHz. In particular, the frequency band primarily used for 4G communication system are located between 700 amhertz and 3 GHz, using both time division duplex and frequency division duplex. More radio spectrum will be vital for the next mobile generation in order to reach the key requirement as proposed before. Consequently, there needs to be an expansion on the frequency band utilized, which can be obtained with the adoption of new band and also by using the spectrum more efficiently. As explained earlier, the spectrum utilized for mobile communication is situated below 6 GHz and is saturated. This means that it's going to be remarkably difficult to find all the amount of spectrum needed available for 5G in frequency ranges. The early introduction of 5G is designed to use the spectrum below 6 GHz. Spectrum above 6 GHz is currently being considered and investigated for 5G use in the near future, ranging from 6 GHz up to 100 GHz, such as centimeter waves and millimeter waves. These bands are not currently being used for mobile communications and therefore represent a great potential to guarantee the target performance value of 5G. So next will be the massive MIMO. The massive MIMO is a multi-user, multiple input, multiple output technology that can provide uniformly good service to wireless terminals in high mobility environments. The key concept is to equip base stations with arrays of many antennas, which are used to serve many terminals simultaneously in the same time frequency resource. The word massive refers to the number of antennas and not the physical size. Massive MIMO operates in TDD mode, and the downlink beamforming exploits the uplink-downlink reciprocity of radio propagation. Specifically, the base station array uses channel estimates obtained from uplink pulses transmitted by the terminals to learn the channel in both directions. This makes massive MIMO entirely scalable with respect to number of base station antennas. Base station in massive MIMO operates autonomously with no sharing of payload data or channel state information with other cells. So talk about the architecture of 5G. We have two, which is the NSA and SA. So the NSA architecture is an intermediate solution that provides additional control and functionalities by making use of the current 4G LTE network. NSA is considered as the early version of SA mode. It's fundamentally concentrated on enhanced mobile broadband, while 5G supported handset and devices like will make use of millimeter wave frequency for increased data capacity, but will continue to use existing 4G infrastructure for voice communications. As it helps mobile network operators such launch 5G quickly for enhanced mobile broadband to get a competitive edge in the telecom market. NSA also helps leverage its existing LTE voice LTE footprint to maximize the LTE installed base and boost capacity while increasing delivery efficiency. It will not support network slicing, but its higher broadband speed will enable services such as video streaming, augmented reality, and virtual reality. So ASA 5G will provide increased data bandwidth by using the following two new radio frequency ranges. The first range is the sub-6 gig, and second range is the millimeter wave. So for the 5G SA, it's a completely new core architecture defined by the 3GPP that introduces major changes such as a service-based architecture and functional separation of the various network functions. Its architecture has definite advantage of end-to-end high speed and service assurance, particularly used for the mobile network operators who are set to commerce new enterprise 5G services such as smart cities, smart factories, or other vertical integrated market solutions. The deployment model enables the rapid introduction of new services with quick time to market. However, it means additional investment and complexities of running multiple cores in the network. The SA5G comprises a new end-to-end architecture that uses millimeter wave and sub-6 gig frequency, and this mode will not make use of the existing 4G LTE infrastructure. The SA5G will use enhanced mobile broadband, ultra-reliable and low-latency communications, and huge machine-type communications to implement multi-gigabit data rate with improved efficiency and lower cost. So what are the 5G applications? I listed three major applications here. The first one is the Internet of Things, IoT. IoT is a network of everyday physical objects, vehicles, applications, devices, buildings, etc. Some examples of the devices that would be part of the IoT are microwave ovens, washing machines, wearable smartwatches, and health monitors. These devices send some information and it is passed on to a remote server, mostly through the internet. The server can also remotely issue commands to control the device. The information collected at the server is then processed to gain knowledge about the underlying process. This knowledge is used to build smart systems like smart homes, smart cities, intelligent transport systems, and healthcare systems, etc. The second application would be the device to device communication. D2D communications will unlock several innovative applications and services. One important application is the area of public safety and security. In scenarios such as the accidents in long tunnels, landslides, and earthquakes, where the cellular network are not available or collapsed, a D2D communication can be readily used for rescue and relief operations. D2D communications will be greatly helpful in machine-type communications, especially vehicle-to-vehicle communications, where it can be used to get information of accidents and other alerts about routes, such as route to finding in self-drive cars. D2D communication can also be used to connect several devices like smartwatches with smartphones. Although other technologies such as Bluetooth also connect devices to mobile phones, a unified protocol will be enable low cost and energy consumption of the device. A third application would be the big data and mobile cloud computing. One of the promising technology of mobile cloud computing is computation offloading, which is a process that allows a remote server or cloud to share part of the computational responsibility that it is traditionally assumed to be fully accomplished by the mobile devices. Since more and more sophisticated applications are installed and running on mobile devices with limited battery life and storage, the amount of computation will significantly drain the battery, which will be unfavorable to users, especially for those smart devices with small size and weight, such as smartwatches. The demand for high-speed data computation, large amount of local storage, and decent standby time will be some of the most competitive features that attract the market. Therefore, one benefit of mobile cloud computing is to help increase the energy efficiency of these mobile devices. So in the last part of this presentation, I will briefly talk about what's the future of 5G and 6G networks. So, which will be empowered by artificial intelligence. So while 5G is being deployed around the world, efforts from industry and academia has started to look beyond 5G and conceptualize 6G. We envision 6G to undergo an unprecedented transformation that will make it substantially different from the previous generation of wireless cellular systems. In particular, 6G will go beyond mobile internet and will be required to support ubiquitous AI services from the core to the end device of the network. Meanwhile, AI will play a critical role in designing and optimizing 6G architectures, protocols, and operators. In the contrast to previous generations, 6G will be transformative and will be revolutionize the wireless evolution from connecting things to connected intelligence with more stringent requirements. So some requirements here are listed below. The first will be the very high data rate, which up to 1 terabit per second. Second would be the very high energy efficiency with the ability to support battery-free IoT devices. Then would be the massive low latency control, which has less than 1 millisecond end-to-end latency. Next will be the very broad frequency band, for example, from 73 gigahertz to 140 gigahertz, and from 1 terahertz to 3 terahertz. Next requirement would be the ubiquitous always-on broadband global network coverage by integrating wireless with satellite systems. And last will be the connected intelligence with machine learning capabilities. So that's all that I want to deliver in this presentation, and hope you guys enjoy this presentation. Thanks for watching. Bye bye.